Today's topic is refraction of light, or simply refraction. Now, refraction is a very important phenomenon, another basic phenomenon related to light, just like the phenomenon of reflection. Already have learnt about reflection previously. Now, similar phenomenon related to light, exhibited by light or shown by light, or similar property shown by light is the property of refraction. What is refraction? Now, refraction simply means bending of light. When this bending of light occurs, when does this property refraction, when does the property refraction or bending of light occurs? Now, consider a light ray passing from one transparent medium into another transparent medium. So here in the diagram we have a glass block here. This is a glass block, easily it can be seen. It's almost looking like a rectangular glass block. SS dash is the surface of the or top surface of the glass block. Now above the glass block only air is present. Now through glass we can see other objects. Such an object or such a medium through which we can see other objects is called transparent medium. Transparent medium is also defined as a medium through which light can pass. We can see other objects through glass because light can pass through glass easily. So this gives the simple meaning of transparent medium, scientific meaning of transparent medium. It's a medium through which light can pass. Even air also, we can see various objects around us through air easily. So air is also a transparent medium. Light can pass through air also very easily. So air here is one transparent medium, glass is another transparent medium. Now light is passing from, say, air into glass. Now PO is the incident light ray, which is incident on the surface SS dash of the glass medium, exactly at the point O. So O is called as the point of incidence, exactly at this point of incidence O. Now PO is called as incident ray because this is the light ray which is incident, that is, which is falling. Incident means falling. PO is the light ray which is falling on the surface S dash at the point O. So PO is the incident ray and O is the point of incidence. Exactly at the point of incidence, imagine a perpendicular. So NO N dash is the imaginary perpendicular. Now this imaginary perpendicular NO N dash itself is called as the normal. It's called as normal to the surface at the point O. Normal to the surface S dash of the transparent medium, that is glass medium at the point O. Now such a normal you have used even in reflection phenomenon also. Previously you have learnt about reflection. There you have used normal NO N dash on a mirror, that is on a reflecting surface. So here on the refracting medium we are imagining a similar normal NO N dash. Now when the light ray PO is entering into the glass medium, that is from air it is entering into the glass medium, it is found that it will not be taking exactly the same direction as the incident ray. Now the incident ray direction is denoted as PO. Now if this direction is extended forward, that is if it is extended further below the point O, this dashed line represents that direction of the extension of the incident ray. This is simply called as incidence direction or direction of the incident ray. Now instead of taking the same direction, now what is happening? The light ray is taking a different direction because it's found that always light bends, exactly it will be bending and takes a different direction. Now this bending, it is found that it occurs exactly at the point O. Point O is also called as the point separating the two media, because above the point O we have air medium, below the point O we have glass medium. So point O is also called as the point separating the two media. Now at this point separating the two media, it is found that bending occurs. Now after light bends at the point of separation of the two media and taken a different direction, now throughout the glass medium it takes a single direction till it reaches some other medium, till it has to pass through some other medium. As long as it's present in the same uniform glass medium, it will be taking again exactly a straight line direction. So bending is occurring only at the point of separation of the two media, only because medium is changing along the path of the light ray. Wherever the medium is changing at the point O only. In the entire path taken by the light ray, medium is changing only at the point O. So only at the point where the medium is changing, there only the bending or bending of light occurs. So that's a very important property related to refraction or bending of light. So from this we can understand the definition of refraction. So refraction simply means what? Bending of light. Where it occurs? It occurs mainly because medium is changing as the light is passing. Whenever it's encountering a change in medium, it's undergoing a bending. Such a bending of light is simply called as refraction. So from this we get the definition of refraction in simple words. Refraction is the bending of light when light is passing from one transparent medium into another transparent medium, and which occurs exactly at the point separating the two media. So this is the simple definition of refraction. So it's the bending of light when light passes from one transparent medium into another transparent medium, occurring at the point separating the two media. That's the simple meaning of refraction. Now it is found that bending or refraction occurs when the medium is changing, only refraction is occurring exactly at the point separating the two media. Now it is found that a scientist by name Huygens, from his own principle simply called as Huygens wave principle, he proved that bending of light occurs mainly because of the change in velocity of light. So velocity of light in air medium will have one value, but in the glass medium it will have another value. Because of this change in velocity, Huygens proved that bending of light will be occurring. So that's another very important thing related to a refraction phenomenon. So what is Huygens wave principle? It actually comes in another topic, another part of the lesson, optics. Optics means simply study of light. So in another part of optics, Huygens wave principle comes clearly. Now now we have the simple definition of refraction. So it's a 2 marks question, very important, objective, very short answer question, 2 marks in different boards, whether it is the state board, any state board, or central board, any board exam. This is a very important 2 marks answer. Now a very important law related to refraction is the Snell's law of refraction. Now there are a few laws related to refraction simply called as laws of refraction. Among them, the most important law is the Snell's law of refraction. Now what is the most important law in reflection of light? You have learned that angle of incidence is equal to angle of refraction. That is, angle of incidence is equal to angle of reflection. I is equal to R. That's the most powerful law in reflection. Now the same function is actually shown by this Snell's law of refraction. That's the most important law of refraction. Now the same topic also gives the definition of refractive index. So for both in any way the answer can be written. Now this is a 4 marks answer, a short answer question. So it can be given sometimes as 3 marks answer also, sometimes even as a 5 marks answer also. 2 parts can be asked from this topic, totally carrying 5 marks also, but mostly it's asked for 3 marks or 4 marks in any board, whether it's central board or state board exam. And it's also a very important topic for the understanding of the behavior of light. It's a very powerful law. So many applications it has. So many applications in light, related to light, are actually based on this very powerful law, Snell's law of refraction. It's a very simple law. Now what does the Snell's law of refraction state? Now it gives the Snell's law of refraction gives the relation between two very important angles called as angle of incidence and angle of refraction. Now angle of incidence and angle of refraction are similar to the laws of reflection you have learnt earlier, angle of incidence and angle of reflection. So here the same thing, angle of incidence is the same, but instead of angle of reflection, here we have angle of refraction. That's all. I and R relation you have learnt in the laws of reflection. The same way in the laws of refraction, very important law of refraction is the Snell's law of refraction. It actually gives the relation between these two angles I and R, which are actually shown in the diagram here. Now what is I? So I meaning is the same again like in earlier the laws of reflection or the phenomenon of reflection. Now PO is the incident ray. The angle made by the incident ray with the normal, this angle is simply called as the angle of incidence. Now once the light ray is entering the second transparent medium, which is actually the denser medium or glass medium, we have seen that by the definition of refraction, it bends, the light ray bends exactly at the point O, which is the point separating the two media, air medium and the glass medium. Exactly at this point, separating point O, separating the two media, light ray bends, and in a different direction. Instead of the original incidence direction or the direction of incidence, instead of taking the same direction of incidence, it's taking a different direction because it's bending. It's taking a different direction and going along the direction OQ. So OQ is the refracted ray. The angle made by the refracted ray with the normal inside the denser medium or inside the second medium is simply called as angle of refraction. Now these are the two simple meanings of angle of incidence and angle of refraction. Now this relation between I and R itself is actually given by the Snell's law of refraction. Now here in the laws of reflection we have seen that I is equal to R, but here I will not be equal to R. The reason is the light ray, incident ray, just observe here, this is the direction of incidence, dashed line here is the direction of incidence. Now this incident direction, which is actually shown by the dashed line here, and the normal, you see there are two intersecting straight lines. Now just observe here, two intersecting straight lines we have here. This is one straight line and the other intersecting straight line. Now these two straight lines are intersecting at this point. Now we have two angles here. What are these two angles called as? Vertically opposite angles. Always from the properties of angles, previously we have learnt that the two vertically opposite angles will be exactly equal. Now just see here, this is the direction of incidence. This is the exact direction of incidence. This is one single line, straight line. Normally another straight line. So this angle and this total angle here between these two dashed lines, the normal dashed line and the direction of incidence, will be the vertically opposite angle. So if the light ray goes just straight without bending, in the same direction of incidence it goes, then this angle and this angle will be exactly equal. So this total angle will be equal to what? I. That's clearly visible here. But now what is happening is light ray is not taking the direction of incidence, but it's bending here. In what direction it's bending? Just observe here. It is bending towards the normal. It is bending towards the normal. This is a very, very important point to remember. In the denser medium, the light ray is actually bending towards the normal. So the angle is now not equal to I. If this is the direction in which the light ray would have gone inside the glass medium, if there is no bending, if there is no refraction, then both this angle and this angle will be, so this total angle should be equal to I. But now it's actually decreasing. So it's decreasing to value here shown as R. So the angle of refraction clearly here is lesser than the angle of incidence here. So they are not equal. Then how R is related to I? That is actually given by the Snell's law of refraction. This also gives the very important quantity called as refractive index. So both are actually present in the almost same diagram, or almost two things we are getting from the same fact. The relation between I and R is actually given by what is called as Snell's law of refraction. That also is nothing but definition of refractive index. Now what is this? What is the Snell's law of refraction? Now that's the important thing. Now now here just one small thing here is, now angle of incidence we are considering in the rarer medium, that is air medium here. Instead of air, even we can consider vacuum also. But how to get vacuum here? Simply whatever air that is present here outside the glass block, we have to evacuate this region. That means complete air should be removed. Then we will be having air and vacuum have similar properties, so we can consider with respect to the behavior of light. So either air can be taken or vacuum can be taken. Now the other medium we have considered is glass medium, which is actually denser compared to air or vacuum. So this angle, which is actually the angle in the rarer medium, is sometimes also denoted as theta rarer. Theta always denotes the general symbol for angle, so theta rarer it's also called as. And the angle in the denser medium, smaller here, which is the angle of refraction here, it is also denoted by symbol theta denser. So these are the other two symbols. So whatever things we are seeing here are simple, nowhere any complication is there. Now what does the Snell's law of refraction state? The Snell's law of refraction, simply the statement is like this. So I'm just moving it a little upwards, so that so here actually below the side heading actually statement will be coming. Here the statement comes. So I'm just here entirely some 67 lines statement will be there. So what is the statement? What is the Snell's law of refraction state? What is the statement of the Snell's law of refraction? Now simply now consider the sine of the angle of incidence. Sine, cos, tan, these are the trigonometric ratios, different three important trigonometric ratios. Now consider the sine value of the angle of incidence. Sine I am taking. Now just observe here, sine I am taking. Sine of the angle of incidence. Now consider the sine of the angle of refraction, sine R. So now take the ratio of these two, sines of the angle of incidence and sine of angle of refraction. Now this can also be called as sine of, so this is the ratio of sine of angle of incidence to the sine of angle of refraction. Now this can also be written as sine of angle in the rarer medium to the sine of angle in the denser medium. This way also it can be written. Now the law simply states that, Snell's law simply states that, Snell found out that this ratio always will be remaining simply equal to a constant. It simply will be equal to constant. Now what is the meaning of this? This simply means that now we can increase the angle of incidence simply. So how to increase the angle of incidence? We have to make the angle, we have to make the incident ray PO to be incident at the point O a little more away from the normal, like this. So just move the light ray like this. I'll draw the light ray somewhere here like this way. That means now it's making its incident at the same point O. It's making still bigger angle away from the normal. That way the angle of incidence can be increased. So now Snell observed that when this angle of incidence is increased, automatically the angle of refraction also R also will be increasing in such a way that always this ratio. So when I is increased here, automatically he observed that R also will be increasing. But he found out that sin I by sin R, that is sine of angle in the rarer medium to the sine of angle in the denser medium, always will be remaining a constant. It will never be changing. What is the maximum possible value taken by I? Light ray, it can be made to be incident at the point O at still more and more away from the normal. Finally, this light ray can be incident at the point O almost parallel like this, almost parallel to the surface. This angle will be almost becoming increasing, will be almost becoming equal to 90 degrees. Now this 90 degrees here is the maximum possible value for angle in the rarer medium, that is angle of incidence. That way I can be increased continuously. Then he found out that R also will be increasing. But always the important thing is angle in the denser medium, that is angle of refraction, R will be lesser than I. Even when I becomes 90 degrees also, R will not be 90 degrees, it will be still lesser. It will be lesser than 90 degrees because always R and I will be such that R will be, because light ray entering the denser medium is bending towards the normal. Due to that reason we have seen that R should be lesser than I. So even that is maintained always in the continuously throughout the increase in I. So R also will be increasing such that R will be always, but it will be lesser than important R, and I increases, R will also be increasing, but in such a way that R will be always slightly lesser than I. By whatever amount it's lesser earlier, always R will be lesser than I, in such a way that this ratio will be always coming to be a constant. So that is what the Snell's law of refraction simply states that. So when a light ray is passing between a rarer medium and a denser medium, the ratio of the sine of angle in the rarer medium to the sine of angle in the denser medium, or ratio of sine of angle of incidence to the sine of angle of refraction, this ratio always remains constant. Now this constant, for example, this constant value exactly for glass, if you take the rarer medium as vacuum or air, for glass this constant value is found to be 1.5. Always for glass, if it's taken in the rarer medium, air rarer medium, or vacuum rarer medium taken as air or vacuum, glass will be always 1.5 only. So this particular constant value is simply, this particular constant value, it's simply called as refractive index of glass with respect to air or vacuum, or refractive index of the denser medium with respect to air or vacuum. Simply it's written as N denser, that means refractive index of the denser medium with respect to the air or vacuum, or with respect to the given rarer medium. Air or vacuum, any rarer medium can be taken as any medium. The only thing is here that medium should be rare compared to the given denser medium. That's all. We can take air here, or water also. Water is also has less density compared to glass. Kerosene also has less density compared to glass. So that way any rarer medium can be taken, not just air or vacuum. But among all the different media, vacuum has the least density because density is exactly 0, because there is no mass. Density basically is defined as mass per unit volume. Density basically is defined as mass per unit volume. Here, actually, whatever density we are considering is nothing but mass density only. mass density only. Now from this particular, one very important thing is, from this particular law, Snell's law of refraction, another important density is defined. Now that density is simply called as optical density. Now, optical density in general is almost same as mass density, but it is slightly different. In certain special cases, it will not be, it can be seen that it's not same as the mass density. So what's the difference between optical density and mass density? A little later it can be seen. Now the important thing is, so the refractive index constant for glass with respect to air or vacuum is found to be 1.5, experimentally determined as 1.5. Like that, for every denser medium with respect to any given rarer medium, this refractive index will be having a fixed constant value. Now why this ratio is constant? What is the reason? This reason for this has been obtained from a very important principle. Just a little earlier, we have seen very important principle. I said Huygens wave principle. Based on Huygens wave principle, the proof has been found out for this. Why Snell's law is correct. So the proof for Snell's law of refraction was given using Huygens wave principle. It's a very simple principle, Huygens wave principle, but though it is very simple, it's very powerful principle, because it can explain many things, not just related to refraction. Many other complicated phenomena related to light were in a simple manner, they were explained by this very simple but very powerful principle called as Huygens wave principle. So from Huygens wave principle, it is found that this ratio of the sign of angle in the rare medium to the sign of angle in the denser medium, it is found to be exactly equal to velocity of light in the rarer medium to the velocity of light in the denser medium. So that's the important thing about Huygens wave principle. Based on Huygens wave principle, it is found that ratio of the sign of angle in the rare medium to the sign of angle in the denser medium, it is same as the ratio of the velocities of light in the rarer medium and denser medium. Now when light is traveling through rarer medium, you have earlier learned that light travels in the form of waves. It has wave nature. It is found to have double nature, both wave nature and also particle nature. Later, more clearly, this will be coming little more clearly in other lessons. So light, you have already learned that it travels in the form of waves. So a wave has its own velocity. So in this rarer medium, light has a certain velocity. That let it be denoted as C rarer. C stands for velocity of, in general, velocity of light denoted by symbol C. So in the rarer medium, let the velocity of light be denoted as C rarer. In the denser medium, the velocity of light, because the medium is changing, velocity of any wave, once the medium changes, will be changing. Like that, light waves also, this will be happening. So in the denser medium, let the velocity of light be denoted as C denser. So this ratio is found to be exactly proved to be equal to the ratios of the velocities of light in the rarer medium to the denser medium. Now this is proved from this Huygens wave principle. Now what about these velocities? Velocity of light in air or vacuum, you have learned that it's 3 × 10⁸ meters per second. So in water, for example, in glass, if we are taking glass as a denser medium, its value is about 2 × 10⁸ meters per second. So they have fixed values. So both these are constants here. Constant by constant is what? It's simply a constant. So that way, from Huygens wave principle, actually we are getting the final proof, that the ratio of final proof of the actual Snell's law of refraction, the ratio of the sign of the angle in the rarer medium to the sign of angle in the denser medium will have to be a constant, because this ratio is equal to the ratio of the velocities of light. Both the velocities in the two media being constants, constant by constant will have to be a constant. This constant itself is defined as the refractive index. So simply called as refractive index of the denser medium with respect to the given rarer medium. So this entire statement itself is called as the final statement of the Snell's law of refraction. So what does Snell's law of refraction state? It's very simple. When a light ray is passing between a rarer medium and a denser medium, the ratio of the sign of angle in the rarer medium to the sign of angle in the denser medium is a constant called as refractive index of the denser medium with respect to the rarer medium. Now just observe here. First we are taking the sign of angle in the rarer medium. Next denominator is what? Sign of angle in the denser medium. But just see here, what is the name? Name is called as refractive index of the denser medium with respect to rarer medium. So there is an inversion here. Just observe here. In the name of the refractive index, an inversion is there. Just remember that we are taking the refractive index of glass. Many times you have learned in the lower classes, that is in the 10th class and 9th class, that refractive index of glass is 1.5. So we are considering refractive index of glass when the glass block is placed in air or vacuum. So we are considering refractive index of denser medium with respect to rarer medium. So this is, the name is not difficult to remember, but when it's expressed in the Snell's law form, it's actually a ratio of what? Rarer to denser. Angle in the rarer to the angle in the denser medium. So always these angles are nothing but angle of incidence and angle of refraction also. That way also it can be remembered. But a more complete form of Snell's law is actually not given as angle of incidence and angle of refraction, but they are just simply called as angles in the rarer medium and angle in the denser medium. This will be more useful. So Snell's law of refraction, even in the most probably in the 9th or 10th class also you have learned, but you have learned it as angle of incidence and angle of refraction. But here it's actually expressed as angle in the rarer medium and angle in the denser medium, because this is much more easier to apply in different complicated situations. Whenever any complication comes, we can come back to the original form, because this is very easy to remember. So refractive index is what? Sine of angle of incidence to the sine of angle of refraction. So a more complete way of stating this is sine of angle in the rarer medium to the sine of angle in the denser medium. So this is a complete statement of the Snell's law of refraction. Also, this also is giving the definition of the refractive index. So whatever things we are seeing here are simple, nowhere any complication is there. So thus we have the complete statement of the Snell's law of refraction, also the complete definition of the refractive index of any denser medium with respect to any given rare medium like air or vacuum. Nowhere any complication is there. So as the equation is very important, I'll just draw a box for the entire equation. So it's a very big equation. So for the entire equation I'm just drawing a box so that the equation will be very clear. So very important equation to be remembered. So the entire statement can be just remembered from this particular equation. Even the definition of refractive index also can be remembered from the same equation. It's very simple. So simple form is sin A by sin R is constant, that is refractive index. So a more complete form is this entire equation, including the in terms of velocities of light in the rarer medium and the denser medium. So that's about the simple statement of the Snell's law of refraction. Now just once observe one small thing here. We are considering the refractive index of, just observe the equation and also the diagram. We are considering the refractive index of any denser medium relative to the, that is with respect to the any rarer medium. That's why this refractive index is also called as relative refractive index. So this is also called as relative. Just observe here, it's also called as relative refractive index. I'm just writing in short form here. Now, always important thing is in the examination, so whatever marks the topic is carrying, even if it's carrying 5 marks, you should be preparing according to the marks. So 5 marks means definitely statement will be carrying 1.5 marks, diagram carries about 1 mark, and the remaining equations, any equations or derivation steps are there, they'll be carrying the remaining marks. So all the steps should be written clearly. So statement of a law is very important. It is something to be by hearted. Even the definitions also, definition of refractive index, or even the earlier 2 marks definitions and statements of laws are the most powerful things in science and technology. They are to be by hearted. They are to be learnt word to word. Entire definition or statement of a law should be by hearted, and everything in the entire lesson will be depending on such definitions and laws only. Once they are understood, every topic related to the lesson can be understood very easily. Any problem related to the lesson can be very easily solved based on the definitions and the statements of the laws. So there are some things to be by hearted. So remaining derivations, everything, they need not be by hearted. They will be coming automatically once the definitions or statements of the laws are applied. In every lesson will be having only 3 or 4 definitions mainly. Main definitions will be, or almost complete number of definitions will be only just 3 or 4, and laws will be just only 1 or 1.5 laws. 1 or 1.5 laws. Half law means something like previous lesson and this lesson together 1 law. Like that, average is taken half law in each lesson. So like that 1 or 1.5 laws only will be there in a lesson. So they are very simple to by heart. So don't think that understanding is more important. Understanding is definitely important, but applying the understanding is even more important. So application of the understanding will be possible only if the law statement of the law or statement of the definition or the actual statement of the definition is by hearted, because every word in a definition is very important and every word in a statement of a law is also very important. So in different situations the same words can be applied, so that's why they have to be by hearted. So it's not difficult to by heart one lesson one definition or one lesson one law. And you know, from these the four definitions belong to that lesson also, one first definition will be most important. The remaining definitions will be almost similar, they will not be difficult to remember. So many topics will be there in a lesson, many essay questions will be there, 5 to 6 essay questions, 7 to 8 short answer questions. Short answer question is something like 4 marks, 3 marks questions, and 10 to 20 very short answer questions, 2 marks questions will be there. They need not be by hearted. They can be easily remembered or written just by using the 3 definitions or 4 definitions and 1 or 1.5 laws. So only these have to be statements and definitions only have to be by hearted. Remaining things will be automatically following from these simple statements and definitions. So you have to prepare your own notes. So once the topic is completed, immediately I'll be just showing the notes also, how to write the notes also. Directly I'll be displaying without wastage of any time. Prepared notes only I'll be putting in the video without avoiding any wastage of time. So now, this is nothing but also the equation for the or defining equation or definition of the relative refractive index, or in simple words refractive index itself. Now usually in most of the situations, refractive index of any denser medium like glass or water or diamond, any transparent medium, is usually considered only with respect to air or vacuum. Now why air or vacuum both are similar? The reason is very simple. Now it can be understood more clearly from this equation. Now velocity of light when the rarer medium is taken as air or vacuum, velocity of light in vacuum is 3 × 10⁸ meters per second. In air also it's almost the same, not much different. That's why air and vacuum are treated the same way. Now in general, refractive index of any medium is considered usually with respect to only air or vacuum. That is found to be the most useful refractive index. Now even other rarer media also can be taken, but this is the simplest refractive index and most useful refractive index. That's why this has been given a special name. When the refractive index of any denser medium is considered only with respect to air or vacuum, it is simply called as absolute refractive index. It is simply called as absolute refractive index. Relative means the rarer medium can be any rarer medium, but if the rarer medium is air or vacuum, then the refractive index is called as absolute refractive index. Absolute refractive, whatever value. So we have already seen example for refractive index of glass is 1.5. That's only with respect to air or vacuum. So it's nothing but an example of absolute refractive index. So now, it's very simple. Now applying the definition for finding a very simple equation and very simple properties of absolute refractive index. So applying the same thing. Now considering, so we are taking water, the rarer medium we are taking it as water, simply air or vacuum. That is air. So I'm writing this more clearly, air or vacuum. So denser medium can be anything. Any medium will be denser compared to vacuum, because vacuum density is, now we are taking only mass density. So actually here optical density should be considered, but optical density is not much different from mass density except in 1 or 2 cases. So we'll come back to that later. So now any medium will be more denser compared to, because vacuum density is 0. So any other medium density will have to be more than vacuum only. So we are considering the rarer medium to be air or vacuum. So the angle in the rarer medium, so angle in the rarer medium is what? Theta rarer. Simply now can be written as simply theta vacuum. And the angle in the denser medium, so angle in the denser medium is what? So this is any medium, so simply it can be called as theta m, or theta medium also I can write it. So any medium we can consider, because any medium is denser compared to vacuum. So then the velocity of light, now just observe here, velocity of light in vacuum. So rarer medium is vacuum and velocity of light in the denser medium is m. C vacuum divided by C medium, Cm it can be written. So what happens to this equation? Snell's law. So applying these two equations in the special case when the rarer medium is taken as air or vacuum. Now we are considering absolute refractive index only. So sin I by sin R can be written as what now? Sin I. I is the angle in the rear medium. So which is theta rear, which is nothing but theta vacuum. It can be written theta vacuum divided by sine of angle in the denser medium. Denser medium is what? Simply any medium. So theta m it can be taken, or theta medium. So in terms of velocities of light, what is the equation? So velocity of light in the rear medium divided by velocity of light in the denser medium. Rear medium is what? C vacuum. So C vacuum I should be writing. So divided by C medium. Now velocity of light in the rear medium, which we are taking it as vacuum, it is found that it's a universal constant. Velocity of light in vacuum is always found to be same for all light waves. That is, for light can have different colors. Vibgyor colors already have learned related to visible light. Visible light is of how many colors? Basic colors 7 colors: violet, indigo, blue, green, Vibgyor colors. And there are invisible light radiations. Below violet there are invisible light radiations. Above red also there are invisible light radiations. So all light radiations, or all light waves, irrespective of their color. Color means color is decided mainly by the wavelength. So irrespective of their wavelengths or colors, all light waves in vacuum, they are found to have exactly the same velocity, c. That value only we have already seen them the value to be 3 × 10⁸ meters per second. That itself is called as velocity of light. It's a universal constant. Already have learned some universal constants previously. Universal gravitational constant, capital G, universal gas constant, capital R, and Planck's constant, small h. So velocity of light is also taken as a universal constant. So C vacuum is need not be written here. Simply it's called as C. So is equal to what now? This is the refractive index of the denser medium. So denser medium is what? Any medium with respect to vacuum. So VAC. So this itself always absolute refractive index is nothing but refractive index of any medium with respect to vacuum or air. So the rear medium need not be specified whenever we are considering absolute refractive index. It's understood that it's only with respect to vacuum or air. So for absolute refractive index, the symbol vacuum is deleted, or some textbooks follow it as air. So the air or vacuum can be deleted. Simply it's called as refractive index of the medium M. So MED can be written, or simply NM can be written. So this is the nothing but the absolute refractive index. So what is absolute refractive index definition now? Simply it's nothing but refractive index of any medium with respect to air or vacuum. So simply the equation is nothing but, in terms of velocities of light, velocity of light in vacuum divided by velocity of light in the given medium. Now observe a very, very important thing. Now whenever a light wave is actually traveling in a rear medium, it is found that it actually can travel faster in a rear medium, but in a denser medium it finds difficulty in moving, just as like ordinary material objects. For example, when a person is walking through air, he can walk normally at normal speed, but supposing he has to walk on a river bed, inside a sea bed, through water he has to walk, then water is more denser medium, more difficulty he will be facing. The same thing is found to be true almost even in case of waves also, so including light waves. So in a rare medium, light waves can travel faster. In denser medium they will be traveling slower. Now just observe here. So numerator we have universal constant. So the refractive index of a medium is inversely proportional to velocity of light in the medium. So in a more denser medium, velocity of light in the medium will be lesser. Means refractive index will be more. So more denser means refractive index will also be more. So glass, we already seen that refractive index is about 1.5. Now water is less density. Less density means automatically velocity will be higher. Less density means, so refractive index will be lower in case of water. So just observe here, density is more, then automatically velocity of light in that medium of higher density will be lesser, so refractive index will be higher. So just observe a very simple thing. Density is more, refractive index is also more. More density, more refractive. What glass has more density, so more refractive. Water has less density, lesser refractive index. So kerosene still lesser density. Kerosene floats on water. Kerosene is also, it's an oil which is transparent, floats on water, so its density is lesser, so its refractive index will also be lesser. Something, I'm just giving an example. Now there are one or two exceptions, I'm just giving it as a simple example. So in general 99% this will be following this. So a medium of higher refractive index, definitely it means that it has more density, and almost definitely it has more density. A medium of lower refractive index, almost definitely it has lesser density. Now except in one or two situations. Now one simple example is turpentine oil. Exception, it's actually an exception, it's not just an example. Almost all the 99% of the materials are examples of this. Higher refractive index means higher density. Higher density means mass density. Now exception of this is turpentine oil. Now for turpentine oil, its density is found to be actually lesser than that of water, but still its refractive index will be higher. So in such a case, that's why turpentine oil is said to have, though its density is lesser, its optical density is said to be greater. So what is optical density now? Optical density is something which tells about the refractive index. Higher the refractive index, higher is the optical density. That's why more accurately we can say that refractive index depends on the optical density. But that's only, so this is actually, so from this we are getting the rough meaning of optical density. What is optical density? It's a quantity which tells about the refractive index of the material. The higher the refractive index, higher is the optical density. In most of the situations, 99.99% of the materials in the universe, optical density is higher when actual density, mass density is also higher, except in case of one or two situations like turpentine oil, etc. So will not be, so whenever we say density means, its real meaning is optical density, but roughly we can take it as mass density itself. So no complication anywhere. So that's about the dependence on refractive index on density of a material. So in simple words, again, in general we can say that higher the density, lesser is the velocity of light in the medium, so greater is the refractive index. So the greater the refractive index is somewhat directly related to the density, which we can roughly take it as mass density itself. So that's the simple thing about the absolute refractive index. Now, so whatever things we are seeing here are simple, nowhere any complication is there. So here we have another very important, very simple equation, the equation for the absolute, that is refractive index of any medium M. Now consider a very simple thing. So in general, now observe this very simple equation. The absolute density, the absolute refractive index of any medium M is nothing but velocity of light in vacuum C divided by velocity of light in the medium. So when the medium is changed, what is happening? Numerator is not changing. Numerator is always fixed, only with respect to vacuum only. When the medium is changed, we are imagining different media, we are considering different media. The velocities of light also will be different in different media. So, but numerator always in this equation will be a fixed constant, which is a universal constant, is nothing but velocity of light in vacuum, 3 × 10⁸ meters per second. So now consider a simple case. Now we'll again consider the relative refractive index. So what is relative refractive index? The refractive index of a denser medium with respect to a rarer medium. Now this equation for relative refractive index is simply nothing but, now just observe here, already we have seen this earlier, refractive index of denser with respect to rarer. In terms of sines of angles of in the denser and rarer medium, it can be seen that there is some inversion. Denser with respect, observe the cursor compulsively. Now here this is an online, something like an online class itself. So compulsorily whatever I am explaining, whatever the teacher is explaining, compulsorily you have to be observing the cursor. So what I am explaining, I am showing with the cursor. So compulsorily concentrate on the cursor without any deviation. So very easily the topic can be, very easily the point can be understood. So our smallest point, however deep the point is, very easily it can be understood once it's a help of a visible, that is help of some equation or board is actually taken. So help of a video is taken actually. So now the refractive index of the denser medium with respect to rarer medium, it can be seen that it is rarer by denser. So first denser with respect to rarer in the symbol actually, but here it's coming as rarer by denser. Even in terms of velocities of light also rarer by denser. So that using this inversion very easily it can be remembered. So refractive index of any denser medium with respect to rarer medium is what? Sine of angle in the rarer by denser. Similarly velocities of light, rarer velocity divided by velocity of light in the rarer medium divided by velocity of light in the denser medium. Simply velocity, rarer medium velocity divided by denser medium velocity. So this, because of this inversion, these two equations, refractive index in terms of angles in the two media and in terms of velocities of light in the two media, very easily they can be remembered. So there is, so inversion is always a little inconvenient, but there is a direct relation also, but and also it's very useful direct relation. Now what is this direct relation for relative refractive index? Very easily in just two steps it can be obtained. So now we are considering the refractive index of a denser medium with respect to rarer medium. Now this now can be expressed in terms of velocities of light, say. So velocity of light in the rarer medium. So the same equation I am writing. So refractive index of denser with respect to rarer is velocity of light in the rarer by velocity of light in the denser medium. So see denser medium. Now I'll just modify this equation slightly, just observe using simple properties of algebra. So I'll write this as 1 by C denser divided by 1 by C rarer. So it can be written easily like this, because 1 by C denser by 1 by C rarer is, take denominator 1 by C rarer to the numerator, will become C rarer by C denser. This way it's something like A by B is 1 by B divided by 1 by A. So again we'll get back A by B this way. Now I'll just multiply this with the, so I want to bring the absolute refractive index. So what is absolute refractive? Just try to remember, absolute refractive index of any medium, Nm. N is the symbol for refractive index here. Absolute refractive index of any medium M is what? Constant velocity of light in vacuum divided by velocity of light in the medium, any medium. So for example, N glass is what? C by C glass. N water is what? C by C water. And N kerosene is what? C divided by C kerosene. So C is something constant. So this way absolute refractive index is expressed in terms of velocity of light in that particular medium and the constant C, universal constant velocity of light in vacuum C. So bring that here. How? So multiply numerator with C, denominator also with C, because absolute refractive index means it requires both C as well as velocity of light in that particular medium, denser medium. So multiplying numerator with C, denominator also with C. Then what happens? Numerator will become C by C denser, which is nothing but absolute refractive index of denser medium, and denominator is what now? C by C rarer. So any C divided by C of any medium, velocity of light in the any medium M is nothing but absolute refractive index. So denominator now is becoming what? Absolute refractive index in the denser, in the rarer medium. Numerator is becoming absolute refractive index in the denser medium. So now, so whatever things we are seeing here are simple, nowhere any complication is there. So this now can be written as what? C by C denser divided by C divided by C rarer. So which is nothing but absolute refractive index of denser medium divided by absolute refractive index of rarer medium. That is what is coming. So therefore what we are getting is a very simple equation. The relative refractive index of denser with respect to rarer is what? Simply it's coming as what? Absolute refractive index of denser by rarer. Now just here there is no inversion here. So here in these two equations for relative refractive index in terms of angles in the two media and velocities of light in the two media, there is an inversion, and refractive index of denser with respect to rarer is what? Rarer by denser in terms of angles, and in terms of velocity of light also rarer by denser. But in terms of absolute refractive index, it is what? Denser with respect to rarer is what? Denser by rarer. So this is very simple to remember. So we have a very simple equation here. The relative refractive index of any denser medium with respect to rarer medium is what? Absolute refractive index of denser by absolute refractive index of rarer. Now this is the next important equation. So this equation, the basic equation, defining equation for refractive index or relative refractive index, it's called as first result. And next, this is simply taken as the second result, which is nothing but absolute refractive index. And this is very important, the third result. All the three equations are very important. So actually when the topic is heard in the class, in any class, whether it's a regular class or online class or a recorded class, it doesn't matter. The important thing is you should be completing your running notes at the same time, because once you are listening to a particular class, second time you should not listen to the class again. So all the details should be taken down as a running notes. But now, you need not take it immediately, because I said I'll make the running notes a little more clearer. Immediately at the end of the topic, I'll just give the full neat running notes within fraction of half minute or so, or a fraction of a second. I'll just display in the next frame itself. I'll display the running notes so that you can take it down immediately. So you need not again change anything. So as it is, all these points will be there. The only thing I'll just add some little sentences, simple. For example, the statement here consists of 3 to 4 lines. Such things I'll just complete so that everything is clear. The same way it can be followed in the examination also. You need not again prepare your separate notes. So as simple as possible, I'll just adjust the running notes. So this is the next very important result related to the refractive index. So this is a simple relation between relative refractive index and the absolute refractive indices for two different media, a denser and a rarer medium. Now all the three equations are very useful equations for determining the refractive indices, that is whether it's relative refractive index, or the second equation is the absolute refractive index of a given medium, and the third is the relative refractive index in terms of the absolute refractive indices of two different media, a denser medium and a rarer medium. Now simple example of this, so all the three equations, but the third equation is actually a very simple equation, because there is no inversion. Denser with respect to rarer, relative refractive index of a denser with respect to rarer is what? Denser by rarer. But the other equations for the relative refractive indices, that is the relative refractive index of denser medium with respect to rarer medium, in terms of the angles it is rarer by denser, in terms of velocities of light it is again rarer by denser. The denser with respect to rarer is rarer by denser. So there is an inversion, but here there is no such inversion. It's a very simple direct equation, and hence this is also very simple to remember. Because of the inversion, we can remember the entire equation 1, and because of there is no inversion, even this equation also is very simple to remember. Now what is the use of this equation can be easily seen from a simple example. Now this is absolute refractive index of the denser medium. For example, we are taking the denser medium as glass. We know the refractive index of glass with respect to air or vacuum is 1.5. The same way refractive index of water, rarer medium, supposing we take it as water, refractive index of water is it's found to be 1.33. It's slightly lesser compared to glass. It is 1.33. So dividing the two, we'll get the refractive index of glass with respect to water. This way, the relative refractive index of any medium with respect to any other medium, that is any denser medium with respect to any other rarer medium, we can get just by knowing the absolute refractive indices of the two media. Now another very simple thing is, just observe here. Now here we have refractive index of denser with respect to rarer. It is simply defined as, in terms of velocities of light, as C rarer by C denser. Now this is the relative refractive index of a denser medium with respect to rarer medium. So from the defining equation we are getting like this. Now the same way refractive index, another less useful thing, actually another less useful thing is that can be obtained. Actually it's not useful much, but still it's not completely useless. Now refractive index of denser with respect to rarer we have considered, because that is useful. Now another thing is, what about the refractive index of a rarer with respect to denser? So from this equation easily it can be guessed that denser with respect to rarer is velocity of light in the rarer by velocity of light in the denser medium. The same way refractive index of rarer with respect to denser is what? Velocity of light in the denser by velocity of light in the rarer. Now just observe this without any confusion. Now Snell's law, Snell found out that the ratio of sines of angle in the rarer to the sine of angle in the denser medium is constant. Why it's constant already we have seen. It's entirely based on Huygens wave principle, because of this relation between the angles and the velocities of light. Because of velocities of light being constant, the ratio will have to be a constant. Now this is defined as what? Refractive index of denser with respect to rarer. The same way, once this ratio is constant, A by B is constant, means B by A also must be a constant. So even if you consider the reverse ratio, that is the reciprocal of this or inversion of this, sine of angle in the denser divided by sine of angle in the rear. That also will be a constant. Just as this is called as refracting index of denser with respect to rear, then this inversion, that is reciprocal of this, is called as refractive index of rear with respect to denser. Refractive index of rear with respect to denser. That way, refractive index of rear medium with respect to denser also has been defined, but that is found to be less useful. Now, one very important thing is, just observe here, refractive index of a denser with respect to rear medium is what? In terms of angles, rear by denser. In terms of velocity of light, it is rear by denser. Already we have seen that velocity of light in a rear medium is always higher compared to denser medium. So numerator here is greater compared to denominator. Numerator by denominator. Numerator being greater, greater by lesser will be greater than 1. So this is very important. See rear. Velocity of light in a rear medium being always greater than velocity of light in a denser medium. Always it can be said that the refractive index. So this is very simple. We are getting a very simple result, but very important. Refractive index of a denser medium with respect to rear medium always comes to be greater than 1. That's what simplest example is always the best example for refractive index is refractive index of glass with respect to air or vacuum. We got it as, we have seen this from almost 9th class. You have been seeing this as 1.5. The same way for water also, many of you remember, it's might be remembering 1.33 like that. So this is the reason why it comes to be a denser medium with respect to rear medium always comes to be greater than. The reason is velocity of light in the rear medium is greater than denser medium. This also gives another important answer for another important question. So already we have seen this in the diagram. When the light ray is passing from denser to rear medium, we have seen that the light ray bends towards the normal in the denser medium. What is the reason for this? The reason for this can be understood like this. This has been already said, it has been explained. Many things in refraction were actually explained, almost everything in refraction, not just refraction. Many things related to light waves have been explained with the help of this very simple principle, Huygens wave principle. So now velocity, C rear being greater than C denser, so it's equal to the ratio of the sines of angle in the rear to the denser medium. Now numerator being greater than denominator, what does this mean? That theta rear is greater than theta denser. So always in the rear medium, when a light ray is passing between two media, in the rear medium angle will be greater compared to the denser medium angle. So this simply means that light ray in the denser medium will be closer to the normal. Angle being lesser with the normal means automatically it means that light ray will be bending towards the normal. That way, always when light passes from rear to denser medium, in the denser medium it bends towards the normal. This is very important result. This is actually one law of refraction. The same way, so here we can see that light passing from rear to denser, it bending towards the normal. The same way it can be proved that if the light passes from denser to rear, it actually bends away from the normal. But that's another situation. We'll not consider that now. That also can be directly obtained from the same equation, but later we'll see that more clearly immediately at the end of this topic. So now these are the things here. So that's the reason why refractive index of denser medium with respect to rear medium will be greater than 1. Greater than 1 values are easy to remember. That's why refractive index is considered only for denser medium with respect to rear medium. Now if we consider the reverse, just see here, what is the refractive index of the rear medium with respect to denser medium? It will be the reciprocal of this. Reciprocal means it will be less than 1. Less than 1 means it will be fraction 1. Less than 1 means something like 0.9, 0.8. Less than 1 fractions are difficult to remember. That's why it's never considered. In 1 or 2 problems, this concept also will be useful. But most of the values, refractive index, see absolute refractive index is what? Refractive index of any medium with respect to vacuum. Any medium is denser compared to vacuum. So this is the best example of the use of denser with respect to rear. That's why mostly refractive index of a denser with respect to rear only is considered than the reverse. So that's the thing. So now coming back to here, this is a direct relation. Denser with respect to rear, relative refractiveness is denser by rear. Numerator and denominator being denser and rear absolute refractive indices. Now these are the 3 very important equations. Now another very simple thing is, just with the help of these 3 equations or 2 equations out of these 3 equations, another very simplified form of the Snell's law of refraction can be obtained. I'll just keep this screen as it is. I just, because only right hand side of the screen will be required actually here mostly, so I'm just keeping the right hand side as it is. I'll just minimize the screen. So I'm trying to take another page, white page, because the white page is actually completed here. So I'll reduce this. I'll just reduce this because I'll be this particular. I just want to continue from this to the next step. Another one or two small steps are remaining here to get the another different form of this Snell's law, a very simplified form of this Snell's law, practically very useful form of this Snell's law. So this as it is I want to put. So I'll just reduce this to minimize this so that only right hand side is visible. So left hand side, you see, this is the equation, the main equation. Only this one I just want to keep. So I'll just minimize this. I have minimized, but left hand side is coming, so I'll just move it to the right hand side, which actually I said will be required. So from here I'm just continuing. So the refractive index of the denser with respect to rarer is, in terms of absolute refractive, is denser by rarer. So from the third equation, this is what the equation, just see, third equation. So from the third equation, just it's very simple, just observe here. So whatever things we are seeing here are simple, nowhere any complication is there. So the refractive index of denser with respect to rarer is, in terms of absolute refractive, it is refractive index of denser, very simple equation, divided by refractive index of rarer. That is the absolute refractive index of denser. When the second medium is not only denser medium, no second medium is considered, not considered here. Not written means it is with respect to value, vacuum. So that's nothing but absolute refractive index of denser medium. This also, second medium is not mentioned. Some rarer medium with respect to what is not mentioned, second medium. Always refractive index means two media are considered. The light is passing between two media. The second medium is not mentioned means second medium must be taken as vacuum. So this is also refractive index of some rarer medium with respect to vacuum. That's nothing but absolute refractive index of the rarer medium. So this now I'll just consider the relative refractive index expressed in terms of sines of the angle. Sines of the angle, denser with respect to rarer is what? Rarer by denser. So sine of angle in the rarer by sine of angle in the denser. So this inversion is already present, already we have seen this. So in terms of absolute refractive index, it is very simple. In terms of relative, that is angles, sines of the angles in the two media, it is inversion is there. Denser with respect to rarer is what? Rarer by denser. Now just observe here, take this this part, write the last two parts of this long equation. There are three things here. There are actually two equations here. This is equal to this, this is equal to this. Now in this I'll just take these two. Now cross multiplying. So just see here, cross multiplying. So take the denser media terms together. Just, it's very simple, cross multiplying. We are just bringing the denser media terms together. So refractive index denser into sine of angle in the denser medium. So this will be simply, and the same way refractive index rarer into sine of angle in the rarer medium. So n rarer, first I will take rarer, into sine of angle in the rarer medium is equal to n denser into sine of angle in the denser medium. That's what is coming. Now here we have already seen that light is passing from the rarer medium to the denser medium. You can just check this in the diagram also once. Check this. Light is passing from where to where? Rarer medium into the denser medium. So in this, so very simple thing, when light is passing from rarer medium into the denser medium, all these diagrams previously we have completed. Rarer medium into the denser medium, what is happening is velocity of light is changing. Next, angle is changing. Angle made with by the light ray with the normal is changing, and refractive index is also changing. Here refractive index has one value, rarer medium. Here refractive index in the denser medium has another value. So initially it is rarer medium, finally it is what? A denser medium. But what is not changing is the product. So n is changing. So what is happening? Rarer to denser, rarer to denser, refractive index is actually increasing from n rarer to n denser. Refractive index value in denser medium, already we have seen that it is higher, but theta is what is happening in denser medium, angle in the denser medium is decreasing. So refractive index is increasing, but angle is actually decreasing. But what is remaining same in both the cases? Can it be guessed? In the first medium, second medium, both the things are changing. Even the velocity of light is also changing. But what is remaining? What is remaining constant? Very simple to guess from the equation itself is visible here. The product is not changing. The product of refractive index and sine of the angle in that particular medium is remaining constant. It's remaining the same. So product of n and sin theta is remaining same. So this is simply written as n sin theta. So it can n into sin theta is equal to same. It's remaining same means it can be written as constant. Constant means something like it's remaining same. So usually same is not used in equations, it's written as constant. So when a light ray or when light is passing from one transparent medium to another transparent medium, this product of refractive index, what is this refractive index? Already we have seen it's absolute refractive index into sin theta in that particular medium, it remains same in both the media. This is a very important result. Which is the, so first angle is what? Already we have seen theta error is what? I, angle of incidence. Theta tensor is what? Angle of refraction. So whether it's angle of incidence or angle of refraction, all that is not mentioned. Just simply states that the product of absolute refractive index and sine of the angle in that particular medium will be remaining unaltered when it's, though light is changing, moving from one transparent medium to another transparent medium. The product of the absolute refractive index and sine of the angle made by the light ray with the normal, it is not changing. So this is found to be practically very useful, because here which is the angle of incidence, which is the angle of refraction is never considered. Just simply angle in the first medium and angle in the second medium. Something like n1 sin theta 1 is equal to n2 sin theta 2. So this is taken as the final form of the Snell's law of refraction. Very practically very useful form of the Snell's law of refraction. So that's the simplified form. This is the simplified form of the Snell's law of refraction. So practically it is found to be very useful. So this is the fourth equation which we are getting. So the first basic form of the Snell's law of refraction we have already seen. Sin I by sin r, just see here, it's visible here. Sin I by sin r is constant, which is simply called as refractive index of the denser medium with respect to the rarer medium. So it's also the equation for the relative refractive index also. And then we have seen the second equation, the absolute refractive index equation, and then third equation, that is the simple relation between the, what is the third equation? Just see the simple relation between the relative refractive index of one medium with respect to another medium in terms of the absolute refractiveness. And finally the fourth equation is this particular equation. Now what is the importance of this equation? Now the importance is, now just observe here, it's not just applicable between two media. So just see here, light is passing from, just see the earlier equation, earlier diagram again. Light is traveling from one medium into another medium. So in such a way that the product of refractive index in both them, that is product of refractive index and sine of the angle in each medium, it is remaining constant. Now next, from the second medium, it's again going into the third medium. So from glass, below the glass some other medium is there. Always Snell's law is applicable mainly between for a pair of media. So second and third also can be taken separately now. Second and third also can be taken separately. Now again in the second and third also, the product always for two particular medium, when light is traveling from one medium into another medium, the product of refractive index and sine of the angle in that particular medium will not be, this product will not be changing. So if it goes into the third medium again, so the second and third media, they again form another pair of media, another set of two media. So for any set of two media, that is for any pair of media, that is any two media, Snell's law is applicable. So now when the light ray is actually passing from second to third, again for second and third separately Snell's law can be applied. Now just observe here, first medium is air medium, theta 1 you take, it can be taken as theta 1. Second medium glass, it can be taken as theta 2. And third medium, it can be taken as theta 3. Now it is possible, just see here, theta 2 is the angle in the second medium. Now when the light ray is actually traveling from second to third medium, again as it passes from second to third, there is another refraction. Already first refraction between the first two media we have seen, there is second refraction between the second and third. So between the second and third media, it is possible, very simple, to adjust the angle in the second medium as the same theta 2. Here see here, theta 2 is already there. Here as light passes from second to the third medium, again here, just observe the cursor compulsorily, second to the third, second medium, again it's possible to make the angle equal to this theta 2. So now this is already, we know it is n2, so angle is theta 2. So in third medium it is n3, angle can be taken as theta 3. then the same equation can be applied for this pair also, second and third media refraction also this can be applied. So then what will be the equation? So already first pair we got n1 sin theta 1 is equal to n2 sin theta 2. When second to third it is what? n2 sin theta 2. The same theta 2 already I said it can be adjusted here as it passes from, as it undergoes second refraction from second to the third medium also. Theta 2 can be adjusted, the same theta 2. How means, any doubt is there? Just wait for a moment, next topic it will be coming. It's very simple, that's the simplest possible adjustment, actually arrangement can be made here. So that here again as it passes from second to the third medium also, the same theta 2 can be maintained here. So n2 theta 2, so it goes to third medium n3 theta 3, then we can apply the same thing. So already we got n1 sin theta 1 is equal to n2 sin theta 2. So here again second refraction n2 sin theta 2 is equal to n3 sin theta 3. So what will be the equation? We are getting extension of this equation. n1 sin theta 1 is equal to n2 sin theta 2 is equal to n3 sin theta 3. Like that it can be extended to any number of media. So this is practically in different situations it will have much more. From this easily it can be said that it can be used for continuous refraction when a light ray is undergoing multiple refractions continuously through different layers of media. So, and another very important thing is many complications which arise from using the regular equation actually can be overcome. They can be avoided just by using this simple equation. Now just consider a very simple application of this. This particular equation gives rise to a very powerful principle in light, an extremely powerful principle in light. What is that extremely powerful principle? Just observe here. Now n sin theta, whenever light is passing between two media, n sin theta, product of refractive index and the sine of the angle in that medium, even when light ray goes to the other medium, this product n and sin theta will be remaining constant. Now just see here, initially angle in air we have seen that it's bigger compared to the angle in the denser medium. Angle in air, rarer medium air, it's bigger. So we'll take this as some 60 degrees, and correspondingly for the rarer medium there is some value of the refractive index. And once it is going into the denser medium, we know that refractive index is increasing, but the angle is actually decreasing. So here if we take 60 degrees, here it can be taken as some 40 degrees. That way it's easy to understand. Now we'll take the reverse. What if the light ray is going in the reverse direction? Just observe here carefully. What if the light ray is taking the reverse direction like this? Just see here in the regular direction, regular refraction, usually we'll take light to be going from the medium to which we are regularly used to is air medium. So any other denser medium we are not used to. For example, water we can't live inside water. Like that, glass also we can't be present inside glass. So we are taking the first medium always as air. So that's the incident medium, and refracting medium is a different medium. So now if we take the reverse, what if the light ray is going from glass into air? But these are also transparent media. Now applying the law here, n sin theta should remain same in both the, so for any pair of media, n sin theta always will be remaining same in both the media of that particular pair of media from Snell's law of refraction. So here, what if the light ray is going reverse? So initially, first angle is what? 40 degrees now, lesser. So refractive index, we know it's of once higher value, refractive index is higher. So n sin theta here should be equal to n sin theta here. So just observe here, observe the cursor compulsorily, n sin theta in this medium. Now this is the first medium, n sin theta in the first medium should be equal to n sin theta in the second medium. What will be this angle now corresponding to this 40 degrees? Already earlier we have taken it as 60 degrees, this is 40 degrees. From Snell's law, supposing we calculate this, it's coming as exactly as 40 degrees. What if the light ray is going reverse? Easily we can guess the answer now. So once it is going, n sin theta here is equal to n sin theta here. So n sin theta here is what? 40 degrees, corresponding refractive index is there. Now once it is going into this medium, what is the refractive index? Already we know, n. And what will be this angle? This angle, n sin theta, will be same in both the cases, only when this angle, second medium angle, should be again 60 degrees. So as the light ray is taking the regular direction, that is rarer to denser medium, 60, 40, if it starts taking the reverse direction, if light ray is passing in the reverse direction, supposing initial medium angle is 40 degrees, the second medium angle, rarer medium angle, should be again exactly 60 degrees. Then only the equation will be, actually if we just use this equation, we'll be getting exactly the same value here. So this simply means that the light ray is exactly taking back the original direction again. It goes exactly at the same angle, means it takes exactly the same path like this. So this way it will be going. So this way it will be going. Now just observe here, what is the importance of this? What is the importance of this particular situation? So light ray is actually going along a path PO, and after refraction it's taking a path OQ. Now if the light ray is taking along, it's going starting in the reverse direction from the this is the entry point, starting point, and this is the exit point, say. If it's starting at the exit point but in the reverse direction, it is exactly retracing the same path in the opposite direction. This is called as reversibility of light. More accurately, it's called as the principle of reversibility of light. It is found to be a very, very powerful principle. It's a very, very simple principle. Directly we are getting it as a consequence of the Snell's law of refraction. So principle of reversibility of light is very simple. If a light ray going along some path is incident at a point, and after deviation, after refraction, it's taking a path, a different path, and reaching some so going through some exit point, say like this. Now if the light ray starts in the reverse direction, so this path 1 we can call this as path 1 and this as path 2. So if the light ray, once again just check this, if the light ray going along a path 1 and incident at a point, and after deviation, that is after refraction, it's taking a path 2. If the light ray starts, if at all it starts along the path 2 in the reverse direction, it again retraces the path 1 in the exactly opposite direction. So this is simply called as principle of reversibility of light. Now this principle of reversibility of light, directly we are getting it as a consequence of Snell's law of refraction. Such a principle of reversibility of light exists even in case of reflection also. Just from the laws of reflection, I is equal to R, incidence angle is equal to reflection angle, from there it can be proved. So this is a very, very important principle of reversibility of light. It has many, many practical applications. Many things will become very simple just by applying the principle of reversibility. So it's not a separate fundamental principle, it's a consequence, or it's derived from the Snell's law of refraction and also the laws of reflection. So I'm not so this is not difficult to remember. The principle of whatever path it's taking, if it starts along the reverse direction at the exit point, it again retraces back its entire path and reaches the entry point as it is in the reverse direction. So it's very simple to remember, so I'm not giving it. So I need not give the statement because it can't be asked in the exam, but it can be remembered very easily as a statement. So what is important in the exam only I'll give in the running notes. So these are the 4 equations related to the Snell's law of refraction, and after the 4th equation we got the very important principle called as the principle of reversibility of light also. I'm just mentioning it as a side heading. So principle of reversibility of light. So that's the consequence of the Snell's law of, or the final form of the Snell's law of refraction. Now just observe here, in the final form, which is the angle of incidence, which is the angle of refraction, nothing is actually important. So now just see here, when it's going in the reverse direction, this is the angle of incidence and this will be the angle of refraction. But still, because the values are not changing in most of the situations, actually this is not taken as I and this need not be taken as R again, because I and R, if they are taken, it will be little, so we can't use Snell's law in the basic form. So for the reverse path, if we take this as angle of incidence, this will become I, this will become R. So that need not be taken. If that is taken, again what happens is here in the same form Snell's law can't be used. So which is angle of incidence, which is angle of refraction, all that is not important. That's why just observe the statement of the Snell's law of refraction, the basic statement of the Snell's law of refraction. The ratio of the sine of angle in, it need not be mentioned as sine of angle in angle of incidence. Angle of incidence means always light ray should be considered to be moving from rarer medium into the denser medium. That's what you have learnt. The basic form of the Snell's law of refraction, sin I by sin R, you have learnt actually long back in the, most probably in the 9th class. Now the final form of Snell's law is this one. In this angle of incidence, angle of refraction, all the names are not important. So just simply it's mentioned as angle in the one medium and angle in the other medium. So n1 sin theta 1 is equal to n2 sin theta 2, which is incidence, which is refraction, all that is not required. So whatever things we are seeing here are simple, nowhere any complication is there. But always simplest equations will be more useful. So any problem comes in this, we again have to come back here, the basic form, but we have to remember that this particular equation, which is actually what, refraction index of denser with respect to rarer medium. It's applicable only when the light ray is passing from rarer to denser. And the final form of Snell's law, this is the final form of the Snell's law. No such thing is required. Light ray can be taken in the reverse direction also. So here actually two arrows are mentioned. In the diagram just see two arrows. So the main direction, most of the topic we have used this particular direction. Now final form, for getting the principle of reversibility of light, we are taking the opposite direction. So whatever it is, see the definition doesn't bother about all those things. Simply it states that the ratio of sine of angle in the rarer medium, I is simply taken as angle in the rarer medium. It's not now called as angle of incidence or angle of refraction, because if the light ray is taken in the reverse direction, this can't be called as, because we are using the same, why we are using the same symbols, because values are same, 60-40, reverse path also 60-40 only. So it's better not to call this as so different symbol. It's better not to use a different symbol here, because same values, so same symbols it's better to use. So always I denotes what? Angle in the rarer medium, and R denotes what? Angle in the denser medium. Then sin I by sin R gives refractive index of what? Denser medium with respect to rarer medium, whether the light ray is going rarer to denser or denser to rarer. Sine of angle in the rarer medium to the sine of angle in the denser medium. Because so due to this reason, many textbooks follow this particular notation. So I is simply taken as angle in the rarer medium, R is simply taken as the angle in the denser medium. They are not called as angle of incidence and angle of refraction because of the principle of reversibility of light. So the ratio of the sine of angle in the rarer medium to the sine of the angle in the denser medium is a constant, simply called as what? The refractive index of the denser medium with respect to rarer medium. Even the reverse also can be considered. Rarer with respect to denser medium, refractive index also can be considered, but that is practically less useful, because the values of refractive indices will be actually less than 1. So they are not actually much used. So if required, any problem is there, any numerical problem if required, we can use it very easily following the same definition. So refractive index of denser with respect to rarer is what? In terms of angles, rarer by denser, sine of angle in the rarer divided by sine of angle in the denser medium. In terms of absolute refractive index is what? It's very simple, equation 3. What is the equation 3? Very simple. Denser with respect to rarer is what? Denser by rarer. That is absolute refractive index of denser by absolute refractive index of rarer. So that's the thing here. So these are the various things related to the Snell's law of refraction, and most very important consequence, which will be actually practically useful in many complicated situations also, is the principle of reversibility of light. Directly we can get it from the fourth equation, which is the final form of the Snell's law of refraction. Okay, now in the next frame, next moment itself, I'll just keep the running notes. So here, just see here, many gaps are there here, you see, some little explanation will be there. Little explanation will be there. I'll just add those explanations. Now before that, just see here. Now how many marks the topic is carrying? 3 marks, 4 marks, or maximum 5 marks. But just see here how many steps of the equations are there. So many steps we got. This many things are not required. So where it's, even if it's given for 5 marks also, actually the explanation should be ended here itself. Just see here itself it should be ended after the absolute refraction. That's sufficient. See here, or even 5 marks also it will be sufficient. One statement, huge statement, big statement will be coming. It's not just 3 or 4 lines, it comes to be about 5 or 6 or 7 lines it will be coming. Statement on one diagram, so many details are there, you see in the diagram, so many details, not so many, too many details are there. And just see the equation, how many stages are there in the equation, see, so many. So the statement carries about 1.5 marks, diagram carries about 1.5 marks, and this step, this equation, very lengthy, so many stages are there in the equation, so many stages are there in the equation. And in the second result also, it's also not a short equation, here also it consists of many stages. So totally 1.5 marks for statement, 1.5 marks for diagram, and 2 big equations, just 2 marks. So that is more than sufficient. Now just see here, this is another half page it is running, and then just see here, this is another half page it is running, which is actually giving finally the principle of reversibility of light. All this is not required, just we are ending the answer for the sake of the board examination point of view. From the board examination point of view, we are just ending the answer, even if it's an essay question, 5 marks. Essay questions in many state syllabi also, they'll be carrying about 5 marks for theory and 2 or 3 marks for problem, even if the total essay question is carrying 8 marks. So more than 5 marks, almost no question will be there. Even if it is there also, this is sufficient, this much is sufficient. Supposing fully totally it's given for 8 marks, refraction Snell's law is never given for full 8 marks, because it's considered as an ordinary short answer question only. So this is sufficient, and remaining things will be coming as a separate note point. How they have to be written in the running notes, immediately in the next frame I will be showing. So this is the actually running notes which actually I'm displaying it directly. Now this running notes you must take down in the notebook immediately after the class. So this is the complete explanation for the Snell's law of refraction and its different forms. We have seen 4 different forms of the Snell's law we have seen. So all these 4 forms. So in the examination only the first 2 forms must be written. The third and fourth forms, so they come under separate note points, so that that's not required in the examination, but they are very important from the examination point of view and also the understanding point of view. So this is the complete running notes. So the best way to take this is you must take the screenshot of this directly from your system or from your phone. Screenshot. Just see here, this is the end of the class. Last 1 or 2 minutes of the class. Class is about 60 minutes or 70 minutes. Last 1 or 2 minutes. This is the class. So just take the screenshot of this. In the first part I'm just moving it. So down, left hand side you observe, and then the right hand side again from the top to the bottom I'm showing. See here the scroll, this is the scroll bar, vertical scroll bar, when to the top, we are at the top of the page. So I'm moving it down, so we will be reaching the bottom of the page. That way it can be recognized. So this is the bottom of the page, even on the right hand side and also left hand side. So observe the scroll bar, and accordingly you take the snapshots, that is screenshots, and then write the running notes, or you can even take the printout also of the screenshot, or I'll be putting the screenshots in the video also. Download link I'll be putting. That is also another way. Directly you can take the printout also, so that to avoid the wastage of time, because it takes some considerable time to write the running notes. So all the points from the examination point of view, they should be noted. So next page, see here, this is the note point. It's giving the third form of the Snell's law. And next, see the fourth form. This continuation of the note point. So the fourth point, that is the fourth form. And then already we have seen from the fourth form, the Snell's law final form is also called. We are getting a very, very powerful principle, the principle of reversibility of light. So just now we have seen the last few minutes, 5 minutes back, we have seen the statement of the principle of reversibility of light also. Now this is almost the same statement I have mentioned here. Now just observe here, the path taken by, it's almost the same, but it's much more simpler. You see, just one sentence coming to be about around 2 lines. It's coming very simple. The path taken by a light ray between 2 points is completely reversible. So this is the simplest possible statement, so that's why I have given this as the complete final statement of the principle of reversibility of light. The path taken by a light ray between 2 points is completely reversible. So what's the meaning of this? Just check it once. From the diagram it can be seen. So you take the 2 points P and Q. So we have seen that firstly it's moving from rarer medium, the light ray is moving from rarer medium to the denser medium. Between the points P and Q it's actually going downwards. Now if the light ray actually starts at the final point, this is the entry point we can just say, and this is the exit point, just for point 1 and initial point and final point. If the light ray starts at the final point but in the reverse direction, this way as shown by the upward arrow here, then it exactly retraces the same path and reaches the point 1 again. That's why the path taken by light ray between 2 points is said to be completely reversible. How it is coming, already we have seen the reason. The reason is the Snell's law of refraction, and another very important reason is the loss of reflection also. This phenomenon occurs, reversibility of light occurs even in reflection also. So whatever be the phenomenon, if light ray can take a certain path between 2 points, say P and Q, its path can again take exactly the reverse path. This from P to Q it can move, means Q to P also exactly along the same path it can move. This is called principle of reversibility of light. Now, this is the simplest form. So that's what is given here. So this is the complete running nodes.